Welcome back everyone to our calc series. Today we are going to talk about implicit differentiation. So previously we've been able to take the derivative of a function. For example, if we had f of x equals x squared, then we're able to go like, hey, I want f prime, and that should be equal to 2x by some of our properties. Now, what has been implicit there, that's not, although this is not what this literally means, what has been implicit there is that we were taking the derivatives of both sides. So we were taking the derivatives of both sides with respect to x. So then the left-hand side would become df over dx, which is just f prime of x, right? So like we're taking the derivative of the left-hand side and the right-hand side, and we're setting them as equal. So implicit differentiation is based on the idea that if you have two equal functions, their derivatives are still equal. If you have two equal functions, then derivatives are still equal. So that is the key idea of implicit differentiation. You differentiate both sides. And the reason why this is called implicit is because in this previous case where we had f of x is equal to whatever, we call that this function is explicitly defined. This function has been defined explicitly. We're told exactly what this function is. But let's say that whatever we're trying to find, let's say y here, is on both sides and we don't have the exact expression to it. Then that's where implicit comes in. So this is like for an implicitly defined function, we want to find its derivative. For example here, we have xy equals x plus y. And we want to find dy over dx. So notice how y here is not explicitly defined, even though we could collect it and isolate it, but this is some good practice. So we want dy over dx, right? And the way we're going to do this is we're going to take the derivative with respect to x on both sides. Okay, and here, so on this left-hand side, we can use the product rule directly. This is equal to the derivative of x times y plus the derivative of y, which is y with respect to x, right? So derivative of y with respect to x times x itself. And this should be equal to, so we have this, sorry, let me, not to get confused with this. So on the other hand, we have d over dx of x, which is 1, plus dy over dx. Then we can collect the like terms, or like we can isolate dy over dx, and that should give us y minus 1 over 1 minus x. So this is one example of implicit differentiation. Again, the idea is to take the derivative with respect to one independent variable, usually the one that you care about, on both sides, and then you want to isolate the dy over dx. So we're going to work through some problems. We have a very short list today, and we're going to do an extra MCQ session. We're going to call this like 3B extra or something. And the idea of this is that implicit differentiation is very frequently covered in MCQ. So like usually there's always one or two of these problems. So we're going to do a huge MCQ session where we're going to cover a lot of these questions just to give you more examples. So if you feel like we don't have enough examples here, please feel free to look up that video. Okay. So here we want d over dx of ln of x. So recall how we said we're going to save ln x for later. So here we're first going to take for granted that e to the x is equal to, the derivative of e to the x is equal to e to the x. All right, we're still going to take this for granted. And we want to find ln x. And so here's what we're going to do. Often to find inverse functions, we're going to need the chain rule. And the idea of this is that we're going to compose a function using e and ln. So what we're going to do is we're going to let actually we're not going to write a function. Consider this function right over here, e to the power of ln x. And this is just equal to x because ln of x is just the power you need to put on e to make it back into x. So this is something that's always true. Now, oh, well, like not exactly because x needs to be greater than 0, but aside from that, this is always true. We implicitly differentiate both sides, and we would find, given this, we would have that e to the, so this is the derivative of this outer one, and then this inner function is ln x, right? So we would have the derivative of ln x, or we're just going to write this as here, this as put in the problem here. So then this is what we're going to solve for. And this is equal to 1. And then we're going to notice e to the ln x is just equal to x, right? So this thing is equal to 1 over x. And therefore, we have found ln x using implicit differentiation and the chain rule. So often you would find that that implicit differentiation is used side by side with the chain rule. Okay, so now we're going to move on to some MCQs. And we're going to start off with this. So again, implicit differentiation, we're going to take the derivative of both sides. So we're going to find that the derivative of a constant is 0, and then this d over dx of xy is equal to y plus x dy over dx minus e to the xy itself times d over dx of xy. That's going to be the thing repeated again, like this. And notice here, this factor here is shared, right? So what we could do is we could just take out this factor because it's just very convenient to use. 1 minus e to the x, e to the xy. So then what we could do here instead is we can just solve for this one, and that's just dy over dx is equal to negative y over x. This is one of the more unusual cases because here you could just directly take out this factor. But usually what you should do is you should just expand out and then solve for dy over dx. But here we have this very nice common factor that allows us to directly solve this. So the answer is D. Okay, what is the slope of the tangent to the curve of this? Again, slope of the line tangent, it means dy over dx, or the derivative of y with respect to x, right? So when y equals 1, so we're given a specific moment. So again, you do implicit differentiation. That's just going to give 2x plus 2 times derivative of xy. That's going to be y plus x dy over dx plus 6y times dy over dx is equal to 0. If I jumped a little bit fast for this last step, notice you first want to sort of the inner layer is y, and then you will first take the derivative of this whole thing with respect to y, and then you take y with respect to x, which is just this thing. So then you can isolate dy over dx. So dy over dx you can find as this, and then you would move the other things to the other side. And then we would find dy over dx is equal to negative 2x minus 2y over 2x plus 6y. Then notice we don't know what x is at the moment, but we could find this easily by plugging y in. So x squared plus 2x plus 3 is equal to 2. And so we would find x is equal to negative 1. So we would plug in dy over dx at negative 1, negative 1, 1, yes. And that would become 2 minus 2 over negative 2 plus 6. That's going to be 0. So C is our answer. Okay, so finally here we have another implicit differentiation. I'm just going to even quicker for this one. 2y dy over dx minus, so here we have one somewhat bigger factor. We want dy over dx of this thing, and that's going to give you 2x y plus 2x squared dy over dx equals 0. And then we can isolate dy over dx. So dy over dx should be equal to 4xy over 2y minus 2x squared. So then we just find, we might want to simplify this because the answers are usually simplified like this, and we check which one corresponds. So it's this one actually. So these are all the problems for today. If you want extra practice, again, go to this extra MCQ session. Thank you.